Logistic regression draws a line between two classes, but it never asks which line is best. When many lines all separate the data perfectly, is one better than the others? The support vector machine says yes emphatically, and the answer leads to one of the most beautiful tricks in machine learning. Picture two groups of points you can split with a straight line. The catch: there are infinitely many lines that do it. One hugs the blue points, another grazes the gold, a third sits crooked in between. All of them get the training data right. So which one should you trust on data you haven't seen yet? The SVM's answer: pick the line with the most breathing room. Draw the dividing line so that the empty corridor on either side, the margin, is as wide as possible. The best boundary isn't the one that just barely separates the classes, it's the one that stays as far as it can from both. Maximum margin, maximum safety. Here's the elegant part: most of your data turns out to be irrelevant. Only the few points sitting right on the edge of the margin actually determine where the line goes. Those critical points are the support vectors. They support the boundary. Delete every other point and the line wouldn't move an inch. The model is defined by its hardest cases. Why obsess over the widest margin? Because it's the most robust. A fat corridor means a new point can land a little off from where you'd expect and still fall on the correct side. A razor-thin boundary, by contrast, misclassifies at the slightest wobble. Maximizing the margin is a built-in defense against overfitting. Real data is messy. Sometimes no straight line separates it perfectly. So SVMs use a soft margin, allow a few points to sit inside the corridor or even on the wrong side, but charge a penalty for each. A knob called C controls the trade-off. High C means few violations but a thin margin. Low C means a wider, more forgiving boundary. Tolerance tuned. But here's the real challenge. What if the data looks like this? One class forming a ring around the other. No straight line on this flat plane can ever separate them. Logistic regression is stuck. The SVM seems stuck too. And then comes the move that makes SVMs famous. The trick is to change the dimensions, lift those flat points up into a higher dimension, give each one a new coordinate based on, say, its distance from the center. Suddenly, the inner ring rises up, the outer ring stays low, and a simple flat plane can slide right between them. Data that was tangled in 2D becomes cleanly separable in 3D. And when you bring that flat slicing plane back down to the original 2D space, it becomes a curve, a circle that perfectly rings one class. By going up a dimension, the SVM drew a non-linear boundary using nothing but a straight cut, lift, slice, come back down. That's the whole idea. The function that defines how to lift the data is called a kernel. The most popular is the RBF or Gaussian kernel, which can carve out smooth curvy boundaries of almost any shape. There is a polynomial kernel for curved but structured data, and others for text and sequences. Choosing the kernel is choosing what kind of higher dimension to imagine. And now the genuinely clever bit, the reason it's called a trick. You never actually compute those high dimensional coordinates. The kernel lets you measure how similar 2 points would be in that lifted space directly with a simple formula on the original points. You get all the power of a huge, even infinite, dimension without ever paying to build it. That's the kernel trick. SVMs are superb on small to medium datasets, especially with many features. They were the dominant classifier before deep learning. The catch? They scale poorly to millions of examples, and the kernel choice takes tuning. But when data is limited and you need a sharp, well-justified boundary, an SVM is still a brilliant choice. So that's the support vector machine. Don't just separate the classes, separate them with the widest possible margin, defined by a handful of support vectors. And when a line won't do, lift the data with a kernel and slice it in a higher dimension. Next time, a completely different style of model, one that asks a series of simple questions, decision trees and random forests. See you there.